Okay, friends, it's 8:30 now, and I would like to welcome you all today again. This Saturday Manufacturing Talks, getting organized by the Center of Excellence in Advanced Manufacturing Technology at IIT. Some of you must be aware that this Center of Excellence has come up recently. Sometime in 2018. This Center of Excellence has been set up with strong support from the Ministry of Heavy Industries and Public Enterprises, and also we have received. We have formed a consortium of the industries, public and the private sectors. So our Center of Excellence is engaged in, the solving the industrial problems, and also engaged very much in giving training to the MSME sectors and the startups. Now, we have started this Saturday Manufacturing Talks. There's a webinar, mega event. We have, they started on 13th of March, and today is the 12th week we are running it. And hopefully we'll be able to continue till 31st of December of this year. So, the Center of Excellence, we are working on four research areas. One is the materials, design and automation, additive manufacturing, and industry 4.0. So the webinar series, we are focusing towards the various the aspects of the advanced manufacturing, the technology. Now we are very fortunate that we had the eminent speakers from the academics as well as from the industry, and we are very much privileged today that we have Professor Shreyes Melkote from the Georgia Tech. Professor Melkote will be talking about the robotic, the machining. So Professor Melkote is a renowned figure in the field of advanced manufacturing across the globe. I'm just going to read out a brief bio sketch of Professor Melkote, and after that, Professor Melkote will start talking about the robotic machining. So Dr. Shreyes Melkote holds the Maurice M. Bryan Jr. Professorships for Advanced Manufacturing Systems in Mechanical Engineering at Georgia Tech. He also serves as Associate Director of the Georgia Tech Manufacturing Institute. Dr. Melkote served as ASME Foundation Swanson Fellow and Assistant Director for Technology at the Interagency Advanced Manufacturing National Program Office at the National Institute of Standards and Technology. Dr. Melkote's current research in advanced manufacturing, focusing towards robotics for manufacturing, physics and data-driven manufacturing knowledge modeling, so it is coming under the digital twin, I believe, and simulation for cyber manufacturing. He has published over 230 peer-reviewed articles in leading journals and conference proceedings. Dr. Melkote serves as Associate Director of the International Journal of Machine Tools and Manufacture, Journal of Precision Engineering and Manufacturing, Green Technology, and the Smart and Sustainable Manufacturing Systems Journal. From 2014 to 2015, he served as the President of the North American Manufacturing Research Institutions of the Society of Manufacturing Engineers. He currently serves on the Scientific Advisory Board of Austrian Center for Digital Production and on the Technical Advisory Committee of the Advanced Robotics for Manufacturing Institute in Pittsburgh. Professor Melkote is a fellow of ASME, SME, and the International Academy for Production Engineering, CIRP. Dr. Melkote received his BTech honors in Manufacturing Science and Engineering from IIT Kharagpur in 1987, Masters from Washington State University in 1989, and PhD in Mechanical Engineering from Michigan Technology University in 1993. He did his postdoctoral work at the University of Illinois Urbana-Champaign prior to joining Georgia Tech in 1995. So you can assume that he is having a very profound knowledge and expertise and association in the field of advanced manufacturing. So we'll be very much eager to hear from Professor Melkote on the robotics in manufacturing. Professor Melkote.
Professor, good evening, I guess, to most of you who have joined. So thank you, Professor Pal, for that very kind introduction, and of course for your kind invitation to participate in the Saturday Manufacturing Talks. It's always a distinct pleasure and an honor to speak to colleagues and students at my former alma mater. And so this is obviously a special occasion for me. I also see colleagues, some of my classmates who are now faculty as well at IIT Kharagpur, other faculty, distinguished faculty from other IITs, including IIT Kharagpur, and one of your senior most alums, my former colleague, Professor Mistry. I see him. He's here. He has joined. So it's nice to see him again. It's been a while. And I also see who I think is the person, Professor P.K. Mishra. I see he has joined, and there's a brief anecdote I'll share about Professor Mishra. Professor Mishra was my BTech thesis advisor. So my association with Professor Mishra is long, and I certainly, my respects to him and my regards to him. It's great to see that he's still extremely active, at least in following advances in manufacturing. I know he was a pioneer in the area of non-traditional machining back in the day at IIT Kharagpur. So it's certainly great pleasure for me to have the opportunity to speak to him as well. I thought I'll, and I see Professor Kumar there as well, my classmate and colleague. I will go ahead and share my slides. See here. If there is any interruption, please bear with me. I'll join again. Hopefully there won't be any interruptions. Just want to make sure that you're able to see my slides.
Yeah. It's fine.
So while probably most of you have some degree of familiarity with Georgia Tech, I thought I'll take a few minutes to kind of introduce Georgia Tech briefly, particularly manufacturing activities at Georgia Tech briefly before I get into the technical portion of my talk. My talk is going to focus on accurate robotic machining, and I think Professor Kant said that, you know, at IIT Kanpur, robotics lab was established back in 1980. So clearly, this is not a new topic necessarily, industrial, but my focus is going to be on industrial robotics and needs driven by industry, particularly the aerospace industry. So without further ado, a brief introduction of Georgia Tech. You know, for those that are not familiar with the Georgia Institute of Technology, it was founded back in 1888, and the first program there was mechanical engineering. The only degree offered was Bachelor of Science in Mechanical Engineering. It was very shop heavy, 5 professors, 5 shop supervisors, and about 130 students or so. The second item that you see in 1903, this may be irrelevant to most of you, but certainly something I share here when I speak. John Heisman, for those of you who have knowledge of American football, the Heisman Trophy is named after him. John Heisman was the first football coach of Georgia Tech. You see the main building, similar to the tech tower that you see at IIT Kharagpur as well. We actually started out as a School of Technology initially, and now we were named Georgia Institute of Technology in 1948. And many of you probably know that Atlanta hosted the '96 Olympic Games, and the Olympic Village, the Georgia Tech was the site of the Olympic Village. So I joined a couple of years prior to that. And then, of course, most of our programs in engineering are well ranked and well reputed. So I will leave the ranking. These things you have to take with a grain of salt. But nevertheless, we have a very strong engineering program at Georgia Tech. Now, talking a little bit about the Manufacturing Institute at Georgia Tech. Georgia Tech has a long history and commitment to advanced manufacturing. A lot of stalwarts in manufacturing, including Professor Boothroyd, for example, some of you may know, and Professor Ramalingam and others have spent time at Georgia Tech in their careers. What you see on the left is a picture of my office building. This is the Manufacturing Research Center building. It's designed like a factory. It's got a high bay you see on the right with like a factory floor where there are large pieces of equipment, manufacturing equipment, etc. That basically different types of interdisciplinary research is carried out. This building is really part of the Georgia Tech Manufacturing Institute, which is one of 11 interdisciplinary research institutes on campus. So I'm a professor of mechanical engineering, but I also am affiliated with the Manufacturing Institute. And we focus on both basic and translational research into next generation manufacturing technologies. And a lot of funding for research here comes from industry, as well as government grants and contracts. All right, oops. Okay, I do not know what happened, but please bear with me. All right. Okay, hopefully now you can see my slides back again. All right, so the Georgia Tech Manufacturing Institute has broadened its scope of activities. These are just snapshots, if you will, or topics, if you will, that are addressed by various faculty from various engineering disciplines on campus and non-engineering disciplines on campus are affiliated, and they work on one or more of these topics. You see precision machining, you see additive manufacturing, you also see public policy, you see IoT for manufacturing, etc. These are obviously topics that are of current interest, many of them, including sustainable design manufacturing. All right, one of the latest additions about 4 years ago to the manufacturing infrastructure at Georgia Tech is the Advanced Manufacturing Pilot Facility. It's about a 20,000 square foot high bay space, but the overall space is about 100,000 square feet. And it's dedicated for translational research and advanced manufacturing, where industry, academia, and potentially government can work together to take the results of basic research and advance it, mature it to something closer to end application. So this particular facility, you see a picture on the top left, which shows the setup that we are using. This is actually part of the Boeing Manufacturing Development Center. Boeing has a presence on campus. It's called the Boeing Manufacturing Development Center, with one Boeing engineer on site to work closely with us on a day-to-day basis. And you see essentially a state-of-the-art robotic machining cell that is there that we make use of for much of the research I'm going to talk about. And then on the right side, you see an image, which is an older image of digital manufacturing capabilities, all the way from hybrid additive manufacturing, subtractive manufacturing, metrology, CT, and all of those capabilities, state-of-the-art capabilities that are there for digital manufacturing. So this is the latest addition to what we are calling the Advanced Manufacturing Innovation Neighborhood at Georgia Tech, where we see the role for academia to actually work closely with industry on site to transfer knowledge and learnings from basic research and mature the technologies into something more advanced that industry can take and apply it in the end. All right, so I'll try to motivate my presentation today, and please feel free to interrupt me if you have any questions or any clarifications. I'm certainly open to any questions you might have. Obviously, robots are not new. Industrial robots have been used in the automotive industry for a long time, actually. And industrial robots have been around, obviously, even in the 60s, manipulator arms have been around. So manufacturing certainly was one of the earliest applications of industrial robots for welding and low force, not zero force type of operations. And there are, of course, advantages to using industrial robots, and particularly from the standpoint of high force applications like machining, where you're doing material removal. There are some advantages in terms of workspace requirements. This is particularly important in the aerospace industry, where you're producing very large structures, and you need to, traditionally, you make use of very large machine tools. I mean, they're extremely large. They are monolithic. They actually occupy a lot of space. They're not very flexible. They cost millions of dollars. So less workspace requirements is afforded by robots, especially industrial robots that might be on a rail, for example, or on a mobile platform. These are becoming more common these days. And then, of course, robots are very flexible. They are multi-axis. They have the ability to be used for machining. And you see here a 500 kilogram payload robot in the video on the top right that is actually being used in a lab for machining a wing rib structure. Okay, essentially some shim material on a wing rib structure. This is part of our setup. Or you can also use robots for inspection. You can have 3D scanners mounted on end effectors of robot arms, and industry is using some of these capabilities. Certainly not doing machining like I'm describing here, but certainly doing inspection and grinding, things of that nature are certainly commonplace in industry today, using industrial robots. But there are challenges, okay? There are challenges for us to be able to use it. And if I can go to the next slide. So what are the limitations that actually motivate some of the work that we've been doing for the last 5-6 years or so here at Georgia Tech? Some of the limitations are that robots, while they certainly have much more flexibility, they can be adapted for different applications. They also require less workspace. They are much more compliant than CNC machine tools, for example. Large compliance implies more inaccuracy in the part features, positional inaccuracy, orientation inaccuracy, etc., both static and dynamic. And that's a problem when you're talking about producing or using robots for machining to produce accurate parts, okay, where tolerances are critical. Also, these are because of the compliance, these robots can vibrate. They are much less stiff, at least 1 order of magnitude less stiff than traditional machine tools. And the vibration characteristics of robot arms are more complex than machine tools. They change with configuration. You change the pose of the robot, you change the dynamic characteristics of the robot. So this poses additional complexity in making use of them for machining type of applications. And then, of course, the characterization of robot arm vibratory behavior is time-consuming and expensive. This is not easy, and you will see some of the work that we have done to address some of these challenges. So these provide some of the limitations that we've been trying to address by developing technologies for accurate robotic machining. Much of it is motivated by the needs of the aerospace industry, where aerospace industry would like to make use of such technologies for assembly of large structures, where you do need material removal in a much more flexible environment. So that is what's driving a lot of this research, both here in the US as well as in Europe and other places as well, I might add. Now, what are possible solutions for low accuracy, which results from the compliance characteristics of the high compliance of these robots? Obviously, we could design a robot that's a lot more stiff. Now, people tried, of course, parallel link manipulators. There are these types of robots that are out there. They're used. They're very fast. They certainly have higher stiffness, but their workspace work volumes can be limited. It tends to lower flexibility. Cost is also higher. You can also reduce the amount of material removed if you want to use this for machining. But that, of course, is not, is counterproductive, because you want to maximize material removal rates, not reduce material removal rates to reduce force. The other approach is to actually somehow compensate for the errors in position of the robot. It's important to note that off-the-shelf industrial robots have very good repeatability. That's why they use them. Repeatability can be on the order of less than 1/10 of a millimeter. But their accuracies, they will never quote you. Robot manufacturers don't quote you on accuracy because it's hard for them to do so. Even well-calibrated robots, accuracies tend to be slightly better than maybe a millimeter, which is, of course, very poor for machining applications, clearly, where tolerances may be on the order of tens of microns. So not good enough. So how do you address the errors in position that result from kinematic errors or from compliance-induced errors of robots? So one is to compensate for the position directly. Use some sort of a position sensor. Of course, there are challenges. There are sophisticated position sensors, position orientation sensors like laser trackers, which we are using in our lab, which you may have noticed in one of the pictures I showed you earlier. they are expensive. They cost $150,000, $200,000 if you want to actually integrate a 6 DOF or 6 degree of freedom laser tracking system. Also, there are occlusion issues, line of sight issues that are challenges. Now, of course, the other approach is to somehow model the stiffness characteristics of compliance of the robot as accurately as you can, which is not easy. The compliance of the robot stems from joint compliance, link compliance, etc. And off-the-shelf industrial robots, you really don't know their construction very accurately. So to be able to measure the stiffness characteristics of the joints, they can be nonlinear as well. Oftentimes we make use of linearity as an assumption, but they can be nonlinear as well. So that's not a very, viable option. It certainly is viable for certain applications, but not for the kind of application I'm talking about. One of the approaches we've attempted in our lab is actually combining a sensing approach with some physics-based knowledge of what happens when you use a robot for machining. Okay, essentially ability to be able to predict the forces or the engagements that result in certain forces that you can measure. So that's the basic idea that I'll describe that we have done in recent past. This approach essentially does not require an explicit position sensor. What it does require is some way of actually measuring the forces in real time and then being able to estimate in real time the engagements of the cutter mounted on the end effector of an industrial robot arm, and then being able to compensate in closed loop, okay, through closed loop feedback. So the idea is to be able to compensate for deflection errors of the robot arising from the compliance by estimating the engagements. You see the cutter engagements in a typical milling operation, like an end milling operation that is commonly used in the aerospace industry. You have engagements in the radial direction denoted by A. You have down here in the middle, in the bottom. And then if you're able to spot my cursor, let me make sure I can switch to a pointer, so that will help. So you can see the radial depth of cut. You can see the axial depth of cut. These, of course, affect the forces. So if you have some way of measuring the forces in real time, you can make use of the basic mechanics of cutting to relate these engagements to the measured forces. So that's the basic idea. So the idea is to be able to measure forces in real time in the X and Y directions, let's say, and then relate them to the engagements A and B, estimate them in real time, and then be able to compensate for the static deflection error of the robot at any point in time. So that's one approach that we certainly have pursued. This is a kind of a flow chart, kind of a rough flow chart, if you will, that's describing what I just described. Essentially, you have some desired tool position as a function of time, which describes the engagements of the cutter A and B as a function of time. The milling cutter, which is the robot end effector, you have some sort of a sensor that allows you to measure the forces in real time. And using this knowledge of the relationship between the engagements and the forces, which comes from the mechanics of the cutting operation, you can estimate the actual instantaneous radial and axial depths of cut, compare them to the desired radial and axial depths of cut, and then alter the position through feedback control. So this is something we've tried in our lab. I'll describe briefly how we go about doing this. For more details, I'll point you to some of the publications that are listed at the bottom of these slides, and maybe later on I can share a PDF version of these slides that will point you to some of the literature. So obviously you have a rotating cutter in robotic milling. It's not as simple as simply taking a platform type piezoelectric quartz dynamometer, for example, that's commonly used in machining research, and measuring forces in real time. Even robots have force torque sensors. Most robots, you can actually mount a force torque sensor, but those have their own limitations. The bandwidths are much lower than what you need for a machining operation like milling. So what we did in previous research, which is described in this paper, we developed basically a thin film polyvinylidene fluorides-based sensor. It's a piezoelectric polymer film that has very high bandwidth, in excess of 10 megahertz, extremely good, sensitivity, on the order of 10 microns per microstrain, and costs very little, $5 a film. Now, this is not used typically for this application. People use them for monitoring the the vibration behavior of bridges, for example. People have tried them for structures like that. Now we adapted this type of a sensing material and developed essentially strain gauge equivalent rosettes. So we came up with rosette structures that allow you to actually mount these rosette structures that you see here on the bottom left on an end mill, the shank of an end mill. There are 3 of them, 120 degrees apart, affixed to the shank of the end mill. You develop essentially a transfer function model between the forces acting at the end effector or at the tip of the tool and the dynamic strains measured by these dynamic strain gauges, if you will. And we have electronics that we have designed and built that allow you to actually wirelessly transmit using, IEEE 802.15.4 type of, conforming standard, like a Zigbee communication standard for, wireless transfer of data. And so we are able to actually, we've developed this in prior work. We have shown that you're able to actually measure the forces in real time, and it compares quite well to a standard Kistler dynamometer. For those of you who've done machining research and have used a Kistler dynamometer, you know what I'm talking about. It's kind of the gold standard for sensing in forces in machining type of applications. So we utilize this for measuring the forces in real time. Here's the setup. Without going into a whole lot of detail, given the limited time, you see here essentially a simulation, actual video that shows you a 6-stop robot, articulated arm robot with a spindle that's machining. I'll play the video again so you get to see it. You can see a second. Okay, I think the video played, but fundamentally what you saw in the video is a sped up milling operation performed by that robot. And the sensors are here, shown here, the electronics is here, all this was built in-house, mounted. And we have a KUKA controller, it's a 210 kilogram payload robot on which we actually had a server program that was running and was communicating with a client program, which was the MATLAB program, which embodies the model that relates forces to the engagements, which is running on a PC. And using RSI, which is the remote sensor interface for a KUKA robot, you're able to communicate and modify the position of the robot in real time in response to the measured forces and the computed engagements. So this is essentially our setup, experimental testbed, a little bit of detail, and I won't, go through all of the mathematics here, but we can estimate the error, instantaneous error due to robot deflection by making use of the mechanics of milling process. Okay, these equations that you see up here represent the average force in the X and Y directions based on the cutting parameters, as well as the instantaneous engagement of the cutter as it's going into the material and coming out of it. So using these relationships, you can measure the average the force in the Y direction, X direction using the sensor I just showed you, and you can estimate the engagement, the radial engagement in this case, A, for a constant axial depth of cut. But you can also modify this to actually compute axial and radial engagements in real time. So this is essentially the gist of the approach that was implemented in that MATLAB program that I described and is running in the PC. And we are altering the position of the robot in real time in response to the measured forces and comparison of the desired axial and radial depths and the estimated axial and radial depths. And what you see here is a simple experiment that was done. I'll orient you here. What you're seeing here is basically the deviation of the machine surface. So it was a step that was machined. You see on the right, a step that was machined by the end mill, and the deviation of the step from the nominal. So the nominal, of course, would be perfect. You see, if you were to do this on a CNC machine tool, which is, at least an order of magnitude stiffer than a robot, you actually would get very little deviation at a relatively low feed, in this case, 1.27 millimeters per second, which is a relatively low feed. Now, if you keep increasing the feed, the deviation from this nominal or this ideal situation increases, and you see the errors increase. They move to the left, shows you the deviation. This deviation is because of the robot deflection, the static deflection of the robot at any instant of time. So these are the average deviations as you increase the feed. And so now this is all open loop with no feedback. Now, if I were to actually implement the feedback control, this is the improvement that we are able to get because of this closed loop feedback strategy that I described that does not require a position sensor. Now, this is not perfect, but there is still an improvement of about 78% compared to what you would get if you were not to use this feedback control. So this was our earliest attempt at actually trying to compensate for these compliance errors using, novel real-time sensing type of approaches, which don't require a very expensive sensor. So this is work that's published in a journal that you see up there, and obviously details are present. Let me switch gears. Now, I talked about static error compensation, but in reality, of course, the process is dynamic. And this video that just ran, and if I could play this one more time, you can give me a second. You can see here the end mill vibrating. If you see, hopefully you're able to see. In this direction, when it's cutting now, it's not vibrating as much. And this is because the compliance characteristics of the robot change as you move in one direction. If you change the trajectory, the stiffness characteristics change because the robot pose changes. So this is the complexity of machining with the robot. Now, if you have tracing curvilinear trajectories like I show you here, you can encounter dynamic instabilities, such as chatter, that most of you who have done machining certainly understand. So here's a measurement of the forces that you see below. Shows you the forces in the unstable region, which was that X direction, the horizontal motion when the robot was moving and you saw the cutter vibrating. And then when it transitions to the Y direction, which is here, in this direction, where the tool was not vibrating, as the robot was not vibrating, the cutting forces are not varying as much, clearly showing you a big difference, even though the feed is constant for both of those directions. So this is illustrating the problem. Now, how did we go about addressing it? And again, I will, in the interest of time, skip the math, but I will just give you the gist of it. The basic idea is as follows. We are monitoring changes in the average force vector. So if you see the bottom left sketch, you see the changes in the average force vector denoted here, which of course is a function of the stiffness characteristics of your structure and the displacements in the X and Y directions. The orientation of this force vector relative to the principal stiffness direction of the robot. The principal stiffness direction of the robot can be obtained from the stiffness matrix of the robot through eigenvalue analysis. And you can see here that the maximum stiffness, which is K max and K min, the angle gamma is the angle of the force vector relative to the direction of principal stiffness. So conceptually, it's easy to understand that if somehow I can minimize gamma so that the force vector that is causing the robot to vibrate is always oriented as close to the direction of the maximum principal stiffness, then you would minimize the displacements, right? That is the basic idea. The idea is to minimize this angle gamma by somehow minimize the angle gamma. The way we go about doing this, of course, and if this angle gamma is greater, then of course you will have chatter. Now you can model this as a undamped dynamic system using the joint stiffnesses of the robot, and you can do eigenvalue analysis to actually determine a chatter criterion. In this case, the type of chatter that you see in robots generally is somewhat unlike what you see in machine tools. It's called mode coupling chatter, which is less common in machine tools unless you're doing a boring bar type of an operation where you do see that happen, or something with a very slender tool, for example. So, regenerative chatter is more common in machine tools, but mode coupling chatter is certainly more common in flexible or compliant structures like a robot arm. So you can actually analyze and determine the chatter criterion. Now, I described to you the basic idea. The basic idea here is to take advantage of the fact that forces that are function of the cutting conditions influence the compliance of the structure, and the compliance of the structure, of course, determines stability. So if you look at the stiffness matrix for a robot, the most generalized stiffness matrix has two terms. The joint stiffness is K theta, and there is another term called K sub C, which is essentially called the complementary stiffness matrix. Sometimes it's also called the conservative congruence transformation that relates the Cartesian stiffness K to the joint stiffnesses K theta. Now this K sub C is generally ignored in most robotic system analysis. But if you don't ignore it, you find that that term is a function of the force. It's affected by the force. Conceptually, think of it as if you apply a force to a mechanical structure, it's going to deform elastically. When it deforms elastically, you're going to actually alter the Jacobian, you're going to alter its Jacobian matrix, in this case for the robot. And as a consequence, you're going to alter its overall Cartesian stiffness. And thereby, you're going to change the magnitude and direction of that stiffness, principal stiffness vector, relative to the force vector. So this is the concept that is being made use of in this strategy to try and change the feed rate, which affects the forces, which then affects this K sub C term. And the K sub C term alters the K, the Cartesian stiffness, and therefore alters the direction and magnitude of this principal stiffness vector K max that you see below. That's the basic idea, all right? That we implemented offline. Obviously, this can be done offline. And this is an example illustration of doing that. Now, I won't bore with all the details. What you can do with this model is you can actually compute a relationship between feed. Think of the only knob that I can control is the feed rate of the robot. And this, I'm trying to actually adjust this angle between the force vector and the direction of principal stiffness for that robot. And it turns out that this gamma versus feed defines a stability, delineates stable regions from unstable region. If the feed in this particular instance that you see, you can see a feed of 1 millimeter per second delineates the unstable region to the left from the stable region to the right. So if I can somehow select a feed that is away from this point of critical stability, then I can actually ensure that chatter can be prevented. That's the basic idea. So I actually alter the feed rate. If you look on the top right, you can see that by changing the feed, I can actually increase the feed above 1.02 millimeter per second or decrease it. I can go from stable to unstable simply by altering this gamma through the mechanics that I described earlier. And an experimental validation of this is shown here. This is basically the cutting force in one direction as a function of feed. And you can see that counterintuitively, by increasing the feed, I actually reduce the force, the variation in the forces, which is counterintuitive. Generally, the forces will increase when you increase the feed rate. But in this case, increasing the feed actually moved me away from the point of instability here on the top right into a stable region. And now I have less deviation in the forces. So this is an illustration of how you can do offline programming by selecting the cutting conditions in order to actually minimize mode coupling chatter instability in robotic milling. Details of this are again in a publication that you can certainly look through. This is further validation looking in the frequency domain of what's happening. You can see here 0.7 millimeter per second was the unstable case where you are exciting the resonant frequency of the robot in mode coupling chatter, which is about 11 hertz for our robot, which is one of the lowest fundamental natural frequencies of the robot. And then, of course, if you were to go to higher feed rate of 1.3 millimeter per second, which is greater than 1.02, as I mentioned earlier, you can see that the energy at that chatter frequency peak is very less now. Okay, so you minimized it substantially. All right. Now, we can also use these types of models actually to do determine stability offline, as I mentioned already, by determining using a safety factor. So this is essentially illustrating the same thing. Again, in the interest of time, I'm just going to tell you that the model that I described allows you to plan the feed rate schedule along a curvilinear path in order to avoid chatter instabilities due to mode coupling chatter. So this is something that we have illustrated and demonstrated. Now, I can use that model. Now, model is good. Obviously, we can whatever we can model, so we can predict and make the system as stable as possible prior to the actual experiment. But keep in mind that we cannot model everything. There are uncertainties in the stiffness characteristics of the robot. The joint stiffnesses could be nonlinear, and we simply cannot model everything. And therefore, we do need the ability to monitor in real time any deviations from what the model allowed us to simulate offline and be able to compensate for it. So we do need an online chatter detection and suppression method. So we've implemented that where we make use of the offline method that I just described for planning the feed rate schedule. And then we use the polyvinylidene fluoride piezoelectric wireless sensor that I described earlier to monitor in real time the forces. We actually make use of a wavelet transform, in this case using a Haar wavelet. Since we know that the resonant frequency of the robot is known ahead of time. If you didn't know this, this would be a little bit more difficult to do. But since we know the resonant frequency of the robot, which in our case happens to be between 11 and 12 hertz for the fundamental mode that is being excited during mode coupling chatter, we can design the wavelet transform to be able to actually identify deviations in the signal when you look at that particular band, frequency decomposition band. So we make use of we design a univariate control chart where we are monitoring the voltages coming out of that polyvinylidene fluoride sensor. And then essentially like a statistical process control chart, we look for deviations from stable cutting. Okay, we define upper control limit and a lower control limit that you see in the bottom right. And when it deviates beyond what is considered to be stable region, you detect chatter. That is how you detect chatter using this PVDF sensor and this algorithm. We've implemented this and then be able to actually I've already showed you the ability to modify the feed rate. And so we can do that. So here's an example of how you can actually simulate toolpath with varying degrees of stability. I mentioned here, when you enter up on the top right, you see that it's stable, but when you change directions to Y direction cutting, it becomes unstable, right? So, or rather, I said that opposite, X direction is actually unstable, and when you go to Y direction, it's stable. And you can see here the forces are much larger and vary quite a bit in the X direction. And then, of course, for the same feed rate, when you change directions, it's not varying much, indicating it's much more stable. And you can see the chatter frequencies are not present. The 11 hertz is not present in this case, in this region. Now, we implemented this chatter detection method in real time to be able to actually detect chatter and then suppress chatter by modifying the feed rate. So this is an example experiment that illustrates that. In this particular case, you're going from in the X direction, obviously chatter starts in this direction. You detect chatter using the algorithm that I described. And then of course, when you switch directions, it no longer chatters. Now you're able to detect chatter that we have demonstrated. We then can actually show that you can do closed loop feedback control by varying the feed rate itself to minimize chatter once you detect chatter using this discrete wavelet transform type of a chatter detection algorithm. And here's an illustration of that. You're moving in the X direction. You notice here that the feed rate is going from 1.5 millimeters per second down to 1.2 millimeters per second. It's chattering in this space. You detect chatter here, and then you switch on the feedback control, and you're moving at 1.5 millimeters per second again. But it will not chatter in this particular case. So this is an illustration of how you might be able to address mode coupling chatter detection and suppression in real time. All right, so I know I've gone through quite a bit. I'll touch upon one more recent topic that we worked on, and then maybe just share with you some of the other things we have done or we are doing, and then I'll stop and answer any questions you might have. I mentioned at the outset that one of the challenges with using robots for high force, time-dependent, time-varying dynamic operations like machining is that the stiffness characteristics and the dynamic characteristics of the robot are pose dependent. So you have access to a very large workspace, but when you go to different points in the workspace, the pose of the robot changes, the stiffness characteristics change, the natural frequencies of the robot change, dynamic characteristics change. Damping also changes, okay? And so how do you actually model this? Now, it's not easy to do. So one of the things we have done is we've used data-driven modeling approaches in this particular case, whether you want to call it machine learning or data-driven modeling or probabilistic modeling. I leave that to you, but fundamentally it's a data-driven approach because while you can certainly use fundamental mechanics-based approaches or dynamics-based approaches, they won't be as accurate as data-driven approaches. Obviously, the ideal would be when you combine data-driven approaches with physics-based approaches. That would be ideal. Now, in this case, what we have done is we have come up with a probabilistic model to be able to actually identify the dynamic parameters, the modal parameters of the robot. Okay, think of them as the natural frequency, damping ratio of the robot, and the stiffness if you'd like, but natural frequency and the damping ratio over a large workspace. And this has been done by doing impact hammer tests, essentially experimental modal analysis at different points in the workspace, and then using a statistical model, and then determining the frequency response functions of the robot at each of these locations in space, and then essentially fitting a regression model, so to speak, in this case, a Gaussian process regression type of a model, which is probabilistic and allows you to then predict the modal properties of the workspace, of the robot within the workspace, which then you can use to predict the dynamic behavior of the robot in Cartesian space at different points in the workspace. So that's the basic idea in this case. And you see our robot here, it's a fairly large industrial robot that is being used. And the methodology, again, is described in the paper in much greater detail for those of you interested in the modeling approaches. But it's essentially a Gaussian process regression, or commonly known as Kriging in the statistical literature, where you essentially force, obviously, you treat the underlying physical process as a Gaussian process, and you basically have data that you've collected, let's say f of x as a function of x for illustration purposes. It varies somehow, in this case shown here. And then, of course, you collect data through experiments, like in our case, using experimental modal analysis. Data already has uncertainty in it. This method essentially allows you to regress through the data. Wherever you know data, uncertainty is lowest. Wherever you don't know data, points in space where you did not sample, of course, uncertainty is greater. And therefore, your ability to predict more accurately is going to be uncertain in those regions. So that's the idea. We use Gaussian process regression using the modal impact hammer experimental data to be able to develop this dynamic model that describes the modal properties of the robot over the workspace. What does it tell us? I mean, I just share with you some typical results. And in the interest of time, I'm just going to skip the animation. What you see here is basically the model that you build allows you to simulate the stiffness characteristics, the natural frequency, and the damping of the robot, which all change in the workspace, unlike a machine tool. And you can see the color code here represents the stiffness value. Going from blue to yellow implies that you're increasing the stiffness. So and then X and Y, your X and Y directions represent the distances from the base frame of the robot, which is the origin of the robot. Think of it as the world coordinate system in this case. And as you extend the arm, the stiffness in the X direction changes, it increases, which is like essentially having a beam and you're pushing on the beam along its axis. You would expect it to be pretty stiff, right? And that's what it's actually describing. The natural frequency shows other characteristics, obviously, and then damping also changes. So this model is able to actually simulate all of these characteristics. Now, once you know these things, you can now describe the time response of the robot in these regions of the workspace. That's the advantage of building such a model. All right, so this is again giving you relative errors using the model and validating it at different points that you did not use originally in building the data-driven model. So this is showing you that the errors are the errors increase as you go to more singular poses. As you have an outstretched arm where you're close to singularity, the errors increase, implying that you need much greater sampling in those regions for your data-driven model to increase the accuracy of that model. So this is something that we have done of late, and then we can use this model to actually predict the tooltip vibrations during a machining operation. Now, for simplicity, what we have done is we have assumed that this model only models the first dominant mode, vibration mode of the robot. In reality, of course, for any mechanical structure, especially a complex structure like an industrial robot, you have multiple modes of vibration. But we ignore the higher order modes, which typically have higher damping anyway, and then focus on the lower order mode, the lowest order mode, which contributes the most to the displacement characteristics of the robot in time. So this is showing you the ability of the Gaussian process regression model. I apologize that you may not be able to read the plot, but it's showing you a comparison. The blue represents the predicted, and rather the dashed represents the predicted, and the blue solid line represents the measured, the frequency response characteristics of the robot. So it's predicting the first mode quite well, and we make use of this mode to predict the dynamic response in a machining operation, like a milling operation, at two different points in the workspace, and then compare them with the peak to valley vibration of the robot, which is in this case being measured using a 6 degree of freedom laser tracking system that we have in our lab that allows you to actually look at the dynamic response of the robot in real time, and then be able to actually compare the predicted using this data-driven model and the measure. Pretty reasonable agreement. Obviously, it's not perfect. We cannot model everything. There are some obvious assumptions being made in our data-driven model as well. But nevertheless, being able to predict most of that vibration allows us significant leeway. It provides us with actually quite a few advantages in being able to actually, come up with a tool path or a path plan that can actually minimize the dynamic displacements of the robot, and therefore improve accuracy at the tooltip. All right, so my almost last slide here. I want to point out that there are a bunch of other things we have done in recent past that you can certainly look up publications. We've also looked at actually dynamic rejection of dynamic vibrations. You're using optimal control strategies. In reality, it's hard to actually compensate for the bandwidth of the control system for the robot is limited. Your ability to actually change the position of the robot at higher frequencies is limited. We cannot on our robot exceed about 20 hertz. So lower order frequencies or resonant frequencies of the robot you can compensate, which we have demonstrated through optimal control strategies in this first work that I list here. But then higher order modes, higher order frequencies are harder to compensate. You need some other methods to do that. We've also done some work on pose optimization. This is offline optimization of the pose using both static and dynamic stiffness models to answer the question, which model would you use when? Under what conditions can I get away with just a static model of the stiffness of the robot versus a dynamic model, like the one I just showed you. We've also done some work more recently on methods to enhance the accuracy of data-driven dynamic model that I just shared over a much larger region of the workspace that you can look up as well. And there's some work we have done, which we haven't published yet, is actually looking at using the laser tracker as a real-time feedback, metrology-aided real-time feedback. This is ongoing work, being able to compensate in real time by looking at the robot through the 6-DOF laser tracker system, using an inertial measurement unit as well for sensor fusion purposes. If you want better state estimation of certain quantities of the state of the robot, certain states of the robot, then you can use that. So these are things that we are still working on. All right, so I'll stop there. This is essentially a summary of what I presented. I know I went through quite a bit. I want to make sure we leave at least 5 minutes here for any Q&A. I want to acknowledge, obviously, I wasn't doing all of this work. My graduate students, they are the ones who work the hardest, and we owe everything as faculty to them. I want to acknowledge their contributions. They are the ones who've done the work. I also want to acknowledge sponsorship of much of this work through the Georgia Tech Boeing Strategic University Partnership and the Boeing Manufacturing Development Center at Georgia Tech, and of course the Georgia Tech Institute for Robotics and Intelligent Machines, where I'm one of the core faculty members as well. So with that, I will stop. I'm again extremely thankful to all of you for taking the time late in the evening to listen to me. I'm happy to answer any questions you might have.
Yeah, thank you, Professor Melkote. It's the wonderful lecture.